heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, hello and welcome everyone to Mount Washington Observatory's Science in the Mountains lecture series. My name is Brian Fitzgerald and I'm the Director of Education here for Mount Washington Observatory. Thank you so much for joining for tonight's program. Really excited to bring it to you. For those of you who are unfamiliar with Mount Washington Observatory, we are a nonprofit member-supported organization with a mission to advance the understanding of the forces that create Earth's weather and climate. And we do that through operating a summit weather station with around-the-clock weather observation and forecasting, by conducting research and product testing programs and projects, and by developing and offering innovative educational programs. Hope you're excited for tonight's program. It will be featuring a topic all about extraterrestrial weather and climate with Lowell Observatory astronomer Will Grundy in just a few minutes here. If you have questions for tonight's speaker and you're joining us through Zoom, please make sure you use the Q&A button. You can find that at the bottom of your Zoom toolbar. Make sure you get your questions in as they come up. We'll save some time at the end for a live Q&A session. If you're joining us on the Facebook live stream, welcome. Thanks for joining us that way. We won't be able to join and actually answer your questions during the program, but we'll make sure to follow up after the fact. And if you'd like to connect with us through Zoom for an upcoming Science in the Mountains program, make sure you sign up for those programs over at mountwashington.org. All righty, well, before we introduce Will here to kick things off, we are going to put together a nice poll that we have for you tonight. So if you're joining us on Zoom, we have 4 different questions for you tonight. One that's a pretty familiar one. We like to know, where are you joining from? Perhaps you're joining from a state within New England. Perhaps you're joining from outside New England, like tonight's speaker, or perhaps from outside the country. Take just a moment to share if you feel comfortable. And then we have 3 great questions from Will tonight that we'll get some answers to eventually here. Second question here is, which of these planets or which of these bodies has the highest pressure atmosphere? Is it Mars, Pluto, Venus, Titan, or Earth? Next question, which of these has stable liquid at its surface like we do on Earth? Is it our moon? Is it Triton? Is it Titan? Is it Ariel? Or is it Charon? And then lastly, which of these doesn't have wind-blown dunes, or at least not that we know of? Is that Mars, Earth, Titan, Saturn, or Pluto? Some good, tough questions this evening, and excited to find out the answers here. Looks like quite a few of you have already participated, so we'll give you just a few more seconds for those of you who'd like to join in on the poll. And we'll close it up here in about 3, 2, 1. Alrighty, let's go ahead and share those results. Well, it looks like there is a close tie here between New Hampshire and folks joining from outside of New England. So New England, great representation all throughout. Certainly a good third of you or more from outside of New England, and even a couple of you joining from outside the country. Thanks everyone for joining tonight's program. All right, which of these has the highest pressure atmosphere? Well, almost half of you said Venus, otherwise pretty evenly split. I won't tell you what my guess was, but I was also somewhat confused here. Which of these has stable liquid at its surface? Well, most of you said Titan, 50% of you did. Triton, the runner-up. And then lastly is, which of these doesn't have wind-blown dunes, at least not that we know of? And about half of you said Saturn, and quite a few of you, 44%, said Pluto, with just a few people saying Mars. Alrighty, well, like I said, I actually don't know the answers, I think, to any of those 3 questions, and thank you for sharing your locations. So Without further ado, I'd love to welcome tonight's speaker, Will Grundy, joining us from the Lowell Observatory out in Flagstaff, Arizona. Hey, Will, can you hear us?
I can, and I've got my camera on, and I still need to share the screen here.
Excellent. Well, I can actually see you and hear you, so we're off to a good start.
Yeah, you guys did pretty good on those quizzes, actually. That's it's good to know that I got people that are going to keep me honest here now.
Oh man, all right, I love it. I can't wait to hear the answers. All right, well, Will, feel free, take it away. Thanks so much for joining and looking forward to the talk.
Okay, so I'm going to talk about weather and climates elsewhere in the solar system, but of course, the Earth is our reference point, so I'm going to tie it to the Earth. Um, and what I'll start with is just a view of the solar system, which is maybe a little more complicated than the one that you learned in elementary school. Um, so I divide the solar system into really three broad zones. And the first zone is the one where we live, where the planets are small and rocky and have metallic cores. And there's also a lot of leftover planetesimals in the asteroid belt, um, which I'm not going to talk about at all today because they don't have atmospheres and weather by and large, but they are very useful clues to the processes of formation of the solar system. In the next zone, you have the giant planets, and they are accompanied by lots of moons, and which are really planetary scale in their own right, and have some of them have atmospheres, and most of them are icy. I call this one yellow. That's Io. That's really kind of a terrestrial planet in the sense that it's rocky and metallic. Um, and then the third zone of the solar system is this region beyond the giant planets where we have uh, quite a large number of small bodies, including some that are planet sized. Um, and it's really underexplored because only really one spacecraft has explored that region so far, but there's a lot of bodies out there. And if you like extraterrestrial geology, there's more surface area out there than there is in the whole rest of the solar system combined in terms of solid surfaces, not the surface of say, Jupiter, which doesn't have a solid surface. Okay, so that's the um, the setting, I guess I could put it. And I'm going to also talk about other key factors that influence climate. Um, for instance, the energy sources that can drive planetary processes, including weather. So sunlight is an important one, and on Earth we have about a little over 1,000 watts per square meter. So that's actually a lot of power. But there's also radiation in other forms from space, charged particles and gamma rays and ultraviolet and so on. Um, Not all coming from the sun, some of it coming from the rest of the galaxy that we live in. There's also impacts occasionally, which can deposit a lot of energy in a very small place and do a lot of damage. But a large impact can also be a source of heat for a long period of time because it injects a lot of heat into the ground that diffuses out slowly. Um, there's also differentiation, which is the um, gravitational sorting of materials by density. So the denser materials end up in the core and they give up their potential energy as they sink, and that energy can, heat the planet and drive, for instance, the plate tectonics that we see on Earth. Um, there's another source of heat from the interior, which is radioactive decay. There's short-lived radioactive elements like aluminum 26 and iron 60 that are uh, only really important sources of energy at the beginning of the solar system's history, but then there are longer-lived ones like potassium and uranium that are still breaking down today and providing heat. And then last, if you're in orbit with something else, you can have a tidal dissipation where the orbital energy goes into heating the interior. And of course, what's super important about energy sources is where they heat and what the timing is. So, for instance, sunlight has cycles where we have the day-night cycle as the planet is spinning on its axis. And then we also have seasonal cycles if the planet's pole is tilted with respect to the orbit plane. Um, so one face of the planet has a zone of continuous sunlit, and the opposite side is continuous darkness for some part of the year, um, you can have a more longer term seasonal heating effect. And I guess yesterday or 2 or 3 days ago, we had our equinox, and so that's the equinox, and this would be the Earth at solstice. And I don't know why the animation isn't working, but I guess we'll move on. Um, so then the other thing to think about is the materials that are available, and some of those will have come from the planet's formation. Some of them may have been delivered more recently. Like, for instance, there's some speculation about the water on Earth having come through bombardment more recent than the original formation of the Earth, although still early in Earth history. Um, Various chemical processes can happen and change the composition of, well, recombine the elements to make new compounds. And of course, there's the things that are in the interior and the things that are at the surface and the things that are up in the atmosphere, and sorted based on their volatilities and their densities. Um, and in order to understand how the planet works, you have to really understand the mechanical and the thermodynamic properties of those materials. And thermodynamics is especially important if there are phase changes. So for instance, we're all familiar with water, which freezes when it gets too cold and turns into steam when it gets too warm. Uh, and when such a phase change occurs, that's crucial for climate, because you put energy into water to make it turn into vapor, and you get that energy back when it turns back into water. So when clouds form and drop droplets, that releases that latent heat. Um, and that's the core of both planetary processes as well as industrial processes. The industrial revolution would not have happened without the ability to um, move energy around in the form of heating up water and making steam and driving turbines and pistons and so on. All right, so this is our planet. We have energy from sunlight, over 1,000 watts per meter squared. We also have the internal heat, but that's much, much, much less on Earth, maybe 90 milliwatts per meter squared. So a bunch of orders of magnitude less, but yet still enough to drive plate tectonics and volcanism and so on. We have a rocky surface. The atmosphere is mostly nitrogen plus some oxygen. And then the oceans are water, and that's important because it's liquid, it's very mobile. Also, it can evaporate into the atmosphere and then be deposited somewhere else. And I live in Arizona, and the Grand Canyon is a pretty impressive hole in the ground. Um, and that's really created through water from the oceans evaporating into the atmosphere thanks to solar energy, and then uh, falling up on land and running back down to the ocean, and eroding the canyon as it goes. And that all happened very quickly on geological timescales. Um, and of course, water can be in three phases on Earth: solid, liquid, and vapor. It's not true everywhere in the solar system, but that's sort of crucial to Earth's climate. So let's look at Venus. Venus is a little closer to the sun, and it has a very, very thick CO2 atmosphere, which acts as a greenhouse and traps heat. So the surface is crazy hot, um, much too hot for water to exist as liquid, for instance. Um, and it also rotates very, very slowly. And in fact, it's the interaction of the thick atmosphere with the surface that has probably slowed it down. Um, and uh, the atmosphere is so thick, it's a little over 90 bars, so 90 times the pressure at the surface of our atmosphere. Um, so when the Soviets sent their landers, this is Venera 13 picture on the surface. It's really more like a bath escape than a spacecraft. It's like a pressure vessel slowly sinking through a very, very thick soup of effectively supercritical carbon dioxide, where the difference between gas and liquid is sort of disappeared. Um, and I guess the last thing is that sulfuric acid can condense higher up in the atmosphere and form these clouds, and that reflects a lot of the sunlight, and yet still it's enough gets through to heat it to very uncomfortable temperatures. Um, the giant planets, if you're thinking about atmospheres in the solar system, the giant planets are the ones that immediately spring to mind because they have very thick atmospheres. Arguably, in a sense, Jupiter and Saturn are nothing but atmosphere, sort of all the way down, although it gets into very exotic material forms at very high temperatures and pressures. Um, Very strong winds, partly driven by internal energy. Wind speeds up to over even 1,000 miles per hour on some of them. Also very powerful magnetic fields due to some of the more exotic high pressure phases in the deep interior forming dynamos. They also spin very quickly, but they have very long seasons. So for instance, Jupiter takes 12 years to go around the sun, Saturn about 30, uh, Uranus maybe 84 or something, and Neptune is 160 4 years. So Neptune's really only actually gone around the sun once since it was discovered um, back in 1848. I'm not actually going to talk a whole lot about these because I'm really interested in the interaction between the atmosphere and the surface, and what can the atmosphere do for the surface, and what does the surface do to the atmosphere. And the interiors of these planets are not very well understood because the pressures are so high, the temperatures are so high that um, they're very hard to simulate in the laboratory, and you could never make a spacecraft that would survive going down to those kind of pressures and temperatures. So there's actually not that much that we know about their deep interiors. Um, but just to give an idea of the complexity of the cloud patterns, various levels of clouds at different heights in the atmosphere formed out of different materials on Jupiter, and some of the continuously varying patterns that you see. This is Neptune, which is bluer because the clouds are deeper down, and you're seeing through a fair bit of hydrogen and helium atmosphere plus some methane, which absorbs the red light. But again, there are comparably complicated uh, storms and small scale structures in the atmospheres that we've only seen 1 year of Neptune so far, so we don't have a good sample yet of what a typical year on Neptune is like, but we'll get there. So now I'm going to turn to Mars, which is a much more Earth-like experience in the sense of a rocky surface with a thin atmosphere, although it's CO2 instead of nitrogen, and water is condensable, so you can get clouds and ice on the surface, polar caps. There's the tilt of Mars, the obliquity of its pole is about the same as Earth. So the seasons are similar to Earth, except that the longer term seasons, the pole oscillates a little bit. And so you get the equivalent of Milankovitch cycles on Mars as well. And they're more extreme on Mars, similar to what happens on Earth with the ice ages and so on. And occasionally you get global scale dust storms. So wind is an important shaper of the surface, and here's a serendipitous shot of a dust devil going by one of the landers, and there's just a myriad form of dunes on Mars. There's some of them, but they're quite diverse. Let's see, this is some of the water which condenses as ice just below the surface. It's hidden from view, but one of the landers, the Phoenix lander, dug a shallow trench, and you could see ice in it, and it slowly faded out over time as it was sublimating away. And this is a crater that happened while one of the orbiters was in orbit, and so they were able to take a picture immediately after the crater formed, and it exposed a lot of ice from the interior. And again, that faded out as the ice sublimated away over the next few years. Um, this is a consequence of the carbon dioxide also condensing out, and carbon dioxide is the main atmospheric ingredient. So it's a little weird that the atmosphere itself freezes out, that we don't have on Earth. Um, but carbon dioxide freezes out at the poles, and that drops the pressure of the planet when that happens. Um, and then it sublimates away in the spring, and you get these very interesting weird landforms as it's sublimating away. And they call this stuff Swiss cheese terrain for kind of obvious reasons. Um, and another thing that it does as it's sublimating away is the sunlight can shine through the carbon dioxide ice and illuminate the ground below and warm the ground below, which causes the sublimation to occur from below the carbon dioxide ice, and it forms cracks and squirts out and makes these jets of entrained dust that then get um, sprinkled out across the ground downstream of each of the jets. And after all of the CO2 is gone, you can see these little spider-like patterns that are gullies that were carved by the flowing CO2 below the ice cap. So that's kind of a neat thing that we don't really have on Earth. Um, Titan has a thicker atmosphere than Earth, about 1.5 bars at the surface. Um, the seasons are and the diurnal cycle is very slow. So Titan's day is 16 Earth days, and it's a satellite of Saturn. So its year is the same as Saturn's year, which is 30 Earth years. So the seasons progress slowly. Um, and there's a lot of haze in the atmosphere because of hydrocarbons in the atmosphere getting illuminated by ultraviolet light from the sun and forming heavier hydrocarbons that stick together and form haze particles. And this is the exact same thing as well, it used to happen a lot more, when you'd fly into the Los Angeles basin and you'd see all that orange muck along the horizon, that's hydrocarbons that were processed by ultraviolet light into heavier organics that's then clumped together to form these haze particles. Um, there was a lander aboard the Cassini spacecraft called Huygens that descended to the surface on a parachute, and this is a mosaic of some of the pictures that it took from during the descent, and this is after it landed on the surface, and these little icy cobbles are maybe the size of your fist or so, not very big. But they're rounded, which means that liquid has flowed across this surface, although it's not flowing there at the time that the picture was taken. Um, and so that's a unique feature of Titan. We don't know of any other place in the solar system yet where liquids are stable at the surface. And most other places, they would either freeze solid or they would evaporate quickly. Um, so that's kind of a very attractive site for exploration because it has some similar processes to Earth, and yet they're different because the materials are different. And this just give you a flavor of the complexity of all of the inputs and outputs to the surface atmosphere environment on Titan. It's really probably just as complex as Earth, um, but it's of course much more speculative because it's far away and we can't, crawl all over the surface and explore. Um, but these are radar images that were taken by the Cassini spacecraft in orbit around Saturn and occasionally doing flybys of Titan. And you can see landforms that look like, mountainous regions with lakes and um, channels and dunes that you can sort of trace the prevailing winds going around these high regions. So there's a lot of familiar looking landscapes, but they're made out of different things, and there's probably some important differences. Um, so stand by for the Dragonfly spacecraft, which is going to get to Titan and fly around the surface in the 2030s, I think late 2030s. That's going to be very interesting. Um, we've been doing laboratory studies of how the lakes behave because we need to understand those thermodynamic behaviors. And one thing that we've seen in the lab is that under certain temperature pressure conditions, mixtures of nitrogen and ethane and methane, ethane, various other hydrocarbons, dissolved nitrogen. Under certain temperature pressure conditions, it'll split into two liquids, just like, oil and vinegar, and under other temperature pressure conditions, they dissolve back into each other. And I'll show you a movie just that's kind of fun of two liquids that are separate, but we're condensing. Is that going to go? Oops. Let's try this. Okay, here goes. So you can see that nitrogen is condensing on the top, but it wants to be in the bottom liquid, so it drips through. The bottom liquid is more dense. Um, so it's kind of neat to be able to see some of these kinds of things, and who knows what influence this has on the behavior of the lakes. Pluto and Triton. So these are much thinner atmospheres, maybe a factor of 10,000 thinner than our own atmosphere. So really quite thin. Um, but they have three different condensable species. So they have the atmosphere itself is able to freeze out. That's the N2. But then there's also carbon monoxide and methane, and both of those are able to condense out, always as ices on the surface. And so you can see that there are, well, you can see from the different colors that there are different things going on in different regions around the surface, and seasonal effects because the nitrogen is the most volatile of the three, carbon monoxide is intermediate, and methane is the least volatile. So if you're freezing them out on the surface and then sublimating them away again, the nitrogen is going to be the first to sublimate off and the methane will be the last to sublimate off. Um, Pluto also has very long days, maybe about 6.5 Earth days, and Triton as well has about 6 Earth day. And they have very complicated seasonal cycles, and I'll show you some of that in a minute. Um, and of course, diverse icy geology that's tied to all of this, and it's all, for the most part, driven by surface-atmosphere interaction. Um, the sunlight is reduced out at the distance of Pluto and Triton by roughly a factor of 1,000 relative to what it is on Earth. So something like 1 watt per meter squared. And the internal heat flow is also reduced because the planet's just that much smaller. Um, but the ratio is such that the internal heat is more relative to the sunlight there than it is on Earth. And you do see all of these kind of tectonic features that are driven by the internal energy too. All right, so I kind of got ahead of myself. Here's Triton, which has essentially the same ingredients as Pluto, but geologically looks quite different. So that's a useful lesson that, it's even the same ingredients at similar temperature, similar distance from the sun, don't lead to the same outcome necessarily. So Triton seasonal cycles, it's basically it's the moon of Neptune, and so Neptune goes around the sun every 165 years. Um, and Neptune's pole is tilted 28 degrees from the sun, so that's not that different from Earth's. But Triton's orbit is inclined 23 degrees to Neptune's pole, and then its orbit precesses around every 640 years. So when the tilt of Triton's orbit is in the same direction as the tilt of Neptune, it'd be up here. And that's when they're positively reinforcing each other. And when they're negatively, they're canceling each other out, Triton would be down here. And it oscillates over that range in a 640-year period. So this is the subsolar latitude on Triton. And on Earth, it would bounce back and forth between plus 24 and minus 24. And on Triton, you have these sort of very mild seasons that are less extreme than on Earth, and then these super seasons that are more extreme than Earth. And it just so happens that right now we're about here. We just finished a major southern summer. The Voyager spacecraft went by about here. So all we've seen is really a major southern summer on Triton. But very soon we'll be coming up on equinox, another couple of decades, and we'll get to see the other hemisphere for the first time. It's been in permanent winter darkness basically since the space age. Pluto's seasonal cycles are pretty complicated too. So unlike most of the major planets, Pluto's, I only put the giant planets on here plus Earth, but Pluto's orbit is very eccentric. And so it actually gets quite a bit more sunlight when it's at perihelion than when it's at aphelion by about almost a factor of 2 because it goes as r squared or falls off as 1 over r squared, I should say. The other thing is that Pluto is tipped over on its side with an obliquity a little bigger than 90 degrees. So when it was discovered, one of its poles was pointed sort of more or less towards the observer in the inner solar system. And it went through equinox in the 1980s. And when the Pluto New Horizons spacecraft flew by in 2015, it was tilted the other way. And that's all of Pluto's orbit that we've seen so far, about half of it since it was discovered. This is the subsolar latitude over the last couple centuries, and you can see that it's very asymmetric, and that's because of the eccentricity of the orbit. It goes slowly out at aphelion and it moves very fast at perihelion. So the seasons around perihelion are fast, and the seasons around aphelion are slow, and uh, and it's a pretty extreme because the subsolar latitude, again, just like Triton, gets up to around 60 degrees plus and minus. On top of that, there's the equivalent of Pluto's Milankovitch cycle, which is a 3 million year cycle, which affects so right now, let me go back. Right now, equinox more or less coincides with perihelion, but that cycles over 3 million years to where, southern solstice might be coincident with equinox, a million years ago. And then, a million years from now, northern solstice will coincide with perihelion. And so the seasons do vary a lot. And the imprint of that must exist in the geology on the surface, but we're still trying to understand that. Um, Triton also has these plumes that were erupting when the Voyager spacecraft flew by, and you can see one of them down here. The plume basically rose vertically into the air. This is sort of an upside down picture. So it's at the near the southern pole, um, about 8 kilometers into the air, and then got blown by the wind for many, many hundreds of kilometers. And there's various hypotheses about how these work. Are they like those Martian spiders where sun shines through the nitrogen ice and warms a layer just below the nitrogen ice that then jets out? Or is it something that's erupting from the internal ocean below, in which case it might be very interesting as a way of potentially sampling whether there's life in that ocean? Or is it something intermediate between the two where it's heat from the ocean, but nitrogen that's doing the erupting? Um, Hopefully we'll get another spacecraft to go back there and figure that out. Triton's geology is similarly weird to Pluto's. This stuff is called cantaloupe terrain for obvious reasons, and there's various hypotheses about how it forms. These are probably volatile ices that are sublimating away, and so you have retreating scarps. Um, and this might be the same sort of thing, or it might be the equivalent of a volcanic caldera. There's an impact crater. There's not very many impact craters on Triton, so that tells you that the surface is fairly young. Um, it does have more energy than Pluto because it has tidal energy from Neptune. So its interior is quite a bit more warmed than Pluto's interior. Um, I'll show you a few landforms on Pluto that are directly related to the atmosphere, and one is these methane capped peaks, which really look just like, snow-capped peaks in the Alps. And there's the methane map showing that it matches up perfectly. But the mechanism is completely different. So on Earth, we have humid air in the lower atmosphere where it's warmer, and that, blows uphill, expands adiabatically, and cools, and it can't hold as much water when it's cooler, so that precipitates out and you form snow on the peaks. But on Pluto, the lower atmosphere is actually quite cold and dry of methane, but it's warmer higher up. Um, and methane is also buoyant in nitrogen, so it also tends to want to rise. Um, and the surface cools itself by radiating to space. There's not really enough atmosphere to do any kind of solid state greenhouse, any kind of a greenhouse effect. So the surface is cold. So if you have surface poking up into the warm atmosphere and cooling radiatively to space, the atmosphere uh, precipitates its methane out on those high points, and also winds flow down the hills because it's a katabatic wind because the surface is cooling it. Um, and if you take that process to extremes, you see these weird bladed terrains, and they only really showed up on the right edge of the encounter hemisphere. But again, they're very methane rich, And it may be that these are actually just being constructed by that same process where you deposit methane on the ridges and it builds ridges, just starting on any high point and builds mountains out of this stuff. And this was an effort to see where else that bladed terrain might exist by looking at the color images, which were lower resolution. This is an elevation map, and it shows that these are some of the highest points on Pluto. Um, so it makes sense that the methane would be freezing out there. Um, but this is comparing the colors, and these kind of colors that we could see in the bladed terrain on the encounter hemisphere are all over the place on the non-encounter hemisphere. So if we had flown by with the spacecraft at a time when so that we would have seen this hemisphere, we might have seen bladed terrain everywhere. And dunes have also been reported on Pluto, and caused by these very vigorous katabatic winds flowing down from the mountains. Um, and again, with the methane map, it shows methane where the dunes are mapped. So it looks like this is sort of methane sand that probably came from the mountains. And you can see there's various deposits that are rich in methane up in the mountains. Um, and then this is just showing how much wind speed you would need to move those particles along once you'd mobilized them. And within a fairly narrow size range, they're consistent with the wind speeds that were derived from global circulation models. So it does seem to hold together. And using the spectroscopy, we were able to figure out that the methane grain size should be around 300 microns. And so again, it all held together. Even further from the sun, Pluto's cousins, Eris and Makemake, and of course I don't have any geological pictures because they're just point sources in a telescope. They both do have moons so that we can use that to figure out how massive they are from the orbits of the moons. From that, we know that Eris has more rock even than Pluto, which means it'll have more internal heat from radioactive decay because the radioactive elements tend to end up in the rocks. It also has a very large eccentricity, such that it would, the difference between the solar energy that's hitting it at perihelion and aphelion is almost a factor of 7. So it's a huge variation. But again, Eris's year is many, many centuries. And so we've only seen it out near, it's out near aphelion now, and we won't see it in perihelion for several more centuries. So don't hold your breath. So the last kind of atmosphere I'm going to talk about is exospheres. And this is really, really rarefied atmosphere, so sparse that molecules won't even collide with each other. They'll just follow ballistic trajectories and be oblivious to each other, which means that you can't have sound waves because you need molecules to bump into each other to propagate a sound wave. And these are quite abundant on smaller bodies in the solar system, like the moon, for instance, Earth's moon or Mercury or many of the icy satellites or the larger Kuiper belt objects. And this could be gases that are escaping from their interiors and spending some time in the surface environment before escaping to space. Or it could be something that was arrived in a impact from a comet, which has lots of water, lots of other volatiles. You could also create it radiolytically with charged particles bombarding the surface and breaking chemical bonds. So for instance, if you bombarded water ice, which is H2O, you can break off hydrogen. And so you could have hydrogen that was temporarily acting as an atmosphere. So there's a variety of ways you could create a very sparse atmosphere like this. I'm going to focus on Pluto's moon, Charon, because it's kind of a cool story what it does to the surface of Pluto's moon. So Pluto loses about 3 pounds of methane to space every second. And that sounds like a lot, but it can afford it. It's actually about the same amount of gas that Earth loses to space. And this is some modeling that was done by a grad student then, Will Hui at University of Texas at Austin, where he modeled how abundant the methane would be and found that it would concentrate around Charon because Charon has a pretty, moderately strong gravitational field. So some fraction, a few percent of the escaping methane will actually get temporarily gravitationally bound to Charon and interact with its surface. And of course, some methane may also originate in Charon's interior. We don't really know. But what happens to a CH4 molecule on Charon? Um, so, the typical temperatures on the day side, at least, are maybe 40 to 60 Kelvin, pretty cold, but too warm for methane to freeze out. So it'll just hop around the surface ballistically because it's too rarefied to collide with another methane molecule. Um, and Basically, when molecules are doing this, they hop, they hit a surface, they stick there for a little while. If it's warm, they don't stick very long. If it's cold, they stick longer, and then they leave the surface. And the distribution of speeds that they leave the surface with is a Maxwell-Boltzmann distribution that gets faster the warmer it gets. And the escape velocity of Charon is this vertical line. I made it probably a little too faint. But you can see that a molecule leaving the surface at 40 Kelvin, basically it's never going to get going fast enough to escape to space. But by the time it's up to 60 Kelvin, a bit of it does escape to space. But you'd have to hop a bunch of times before you'd finally escape to space. So you get to bounce around the surface a fair bit. And if it ever finds a cold place, less than maybe 25 Kelvin or something, it'll just stick and stay there. The other thing that can happen to it is it could be ionized. But the ultraviolet light will do that, but the flux of ultraviolet is a lot less, that far away from the sun. So the average life expectancy of a methane molecule might be about a year, an Earth year, before it would get ionized. So it can bounce around a lot before either being lost to space or ionized. Um, this is the temperature history of the surface of Charon, and basically at the equator, this is as a function of time in the last couple of centuries. And the top curve is the daytime maximum and the bottom curve is the nighttime minimum. And so at the equator, you're always getting some sun every day. And so you basically just oscillate between the daytime minimum and maximum. And the coldest it ever gets is maybe 33 Kelvin, which is too warm for methane to stick. But if you go to higher latitudes, you can get down to much colder temperatures. And if you're at the pole, you can stay below 25 Kelvin for a century or more. And so that's a cold trap. And the methane bouncing around the surface will find its way to the pole by just ballistically hopping around. And it'll just stick there and be exposed to the radiation from space and potentially get photolized. And it's sticking there for more than a century. That's plenty of time to get photolized. Um, so uh, uh, and then this is some modeling that was done just a couple of years ago, where they looked at the pressure of Charon's atmosphere, and it spikes each time one of those poles, one of those winter poles, comes around into the spring, and the heat goes up very, very quickly, and all of that methane sublimates away. And so the pressure spikes up, but then it starts condensing again on the other pole. So the blue curve here is the amount that's accumulated on the surface. The red curve is the atmospheric pressure, which only just has these intermittent spikes. And the dashed curve is how much is being photolized. And the net result of the photolysis is that you're creating more complicated, heavier molecules. And that's what paints Charon's poles red. So there's an atmosphere that's even so rarefied, you wouldn't even maybe think of it as an atmosphere. And yet it uh, completely changes the way the planet looks. Um, Another exosphere is Callisto's. This is one of the moons of Jupiter. And there it's water ice plus a lot of dark stuff. And the water ice accumulates in cold traps as everywhere. And what makes an area colder would be higher albedo. So basically, if the water ice is white and the darker stuff is black, the water ice itself is the best place for more water ice to condense, so it concentrates itself. Um, and the other thing is that if you've got a small hill, it can see more of dark space than if you're down in a valley where you're seeing partly the warmer surface nearby. So the coldest places are high albedo, icy places at the tops of hills, and those grow and turn into these crazy looking spikes. Um, And again, this is the effect of a extremely rarefied atmosphere, and yet working over geological time, it can really have a huge difference on the surface. Um, and then the last one is the one of the Uranian satellites, Ariel, where we see CO2 on their surface. All of the Uranian satellites, but the most on Ariel, and we don't really know where it is, and we know that it can move around on seasonal timescales. The best imagery that we have is from the Voyager spacecraft back in the 1980s, but they didn't have any infrared spectrometer, so we couldn't see where the CO2 ice was. Um, and I'd really love to see up close, with similar resolution to what we see in the various Mars spacecraft, what that CO2 does to the surface of Ariel. I'm sure it does something interesting, but we don't know yet. So I'll leave you with a mystery. Um, and something to look forward to. And now, I guess I don't know how to read the question, so maybe you could help me with that, Brian.
Yeah, absolutely. Thank you so much, Will. Yeah, let me just change the view around for everybody. Um, yeah, absolutely. I know we have at least one very detailed question for those of you following along, and I'm sure there are questions galore. Don't forget to use the Q&A button on the Zoom toolbar there and enter a question because I know I at least have several too. But we can kind of kick things off with a question from Rick, who I'll just read verbatim. Rick was mentioning carbon dioxide on Venus and the greenhouse effect. And Rick says, I was under the impression that much of the atmospheric temperature profile is due to adiabatic effects and high in the atmosphere where the pressure is about 1 bar is warm for us, but not enough to melt us. How much does the hot surface's infrared radiation affect the temperature profile on Venus?
Yeah, that's a good question. It's certainly true that the temperature profile cools as it goes higher, but that radiation is streaming through, and some of that radiation is being blocked because CO2 absorbs it. Um, but if heat is trying to escape and uh, and it's blocked, essentially what happens is the heat builds up until it's able to radiate at a different frequency and then it gets out. So a lot of what's actually escaping from the radiation that's escaping from Venus is near infrared, which doesn't get absorbed by the CO2, so it doesn't heat the CO2. But as soon as it were to cool off, it would then be trying to radiate at longer wavelengths that would get blocked by the CO2. So it's in a balance. Um, but yeah, I mean, if we had a balloon or something that could exist in that upper atmosphere around where it's 1 bar and comfortable pressure. It's also a moderately comfortable temperature, and apart from the sulfuric acid and all of that. But yeah, you could have a space station there.
There you go. Yeah, I'm sure we could engineer a solution to that one. That's so fascinating. And well, another question here from Bill, who's curious. What do we know about wind speeds on planets or moons with lower solar load than Earth? Is there like a consistency across those planets or moons, or is it really vary?
Right. Um, so on Titan, for instance, the wind speeds are quite slow, and part of that is that it's a relatively thick atmosphere, and there's not that much solar energy driving it. Um, On Pluto, the wind speeds are a little faster, but not out of spec for Earth. Tens of meters per second, maybe meters per second. Um, it also depends on what the wind is flowing over, of course, and if it's flowing over a rugged surface, that will impede it. So the close to the surface, the wind speeds tend to be lower, and uh, higher up in the atmosphere, they'll tend to be faster. Um, And you do see super rotating winds in a lot of places where the wind actually goes faster than the spin rate of the planet. Um, I'm not really a I'm not one of the guys that does the GCM modeling, so they could answer that better than I could.
Oh, it's fascinating though. I mean, just from a general sense, I mean, how is it that yeah, I mean, how are those things calculated or sort of remotely sensed in the first place? I'm wondering if maybe you can explain that a little bit.
Right. So if you can see clouds, you can track them moving, and that's how it's been done on all of the giant planets. You could also do Doppler techniques if you're looking at a spectral feature in the wind and a spectral feature in the atmosphere, and you look at, say, the limb on one side and the limb on the other side, and you compare the Doppler shift. You can get, the profile of whether the wind's coming towards you or going away from you.
Yeah,
Um,
I mean, yeah, not I guess not too different from remotely sensing our own planet to a certain degree, right?
yeah, but in many places it's never been measured. Like, for instance, we didn't have any instruments that were suitable for measuring it aboard New Horizons. I keep coming back to that because I was involved with it. So, but so we were not able to measure the wind speeds on Pluto, and the numbers that I was quoting are coming from GCM models where we put in, the same uh, heat sources that we know about, um, and the orbital parameters, and just see what the atmosphere does.
Oh,
But that may
interesting.
or may not be right. It depends on the model.
Some of it, I guess, is theoretical, huh? Well, I'm really curious. I know you got right into it, but I mean, I don't actually know a ton about your background. I'm wondering how did you get into astronomy and kind of wind up where you are today?
Right. So I started grad school in the late 1980s, and I did planetary science at the University of Arizona. And I really did that because I liked physics, I liked chemistry, I liked geology, and I couldn't decide. And it seemed like a way of getting it all, right?
Oh,
So it was the interdisciplinary nature of it that attracted me. And then like the year after I started grad school was the Voyager flyby of Triton, and it was like, okay, clearly these guys are having all of the fun, and there's only one left, Pluto. So let me focus on that a little bit and see if I can if I can worm my way into that.
well, so I'm curious. I was mentioning before when we met up before the program. I've been out in the Flagstaff area, but not fortunate enough to visit you guys at the Lowell Observatory. I'm wondering, can you just share maybe a little bit about what goes on at the observatory there? Obviously, a different, not a meteorological observatory,
Yes, but we're
more
very
common
affected
use.
by meteorology.
It is, and hence why maybe some people get a little confused by the term in both cases. But nonetheless, I'm curious. What is some of the I guess active research sort of programming that goes on? I mean, there's just in the little that I know, you all do quite a bit there.
Yeah, so it's an interesting institution in that it has a lot of science going on and also a lot of public outreach going on under one roof. Um, so it's really we're just completing this new Astronomy Discovery Center, which you should definitely visit if you're in the area. It's going to be a really impressive facility. Um, and so there's a lot for the public to do. There's a whole bunch of telescopes that are under a protected roof during the daytime, and we roll off the roof so you can look at different things in the sky. Um, and Flagstaff, of course, is a dark sky site where relatively early on legislation was passed to try to discourage people from shining their lights up into the sky, and that's managed to be protected still. And you can just go outside your house at night and see the Milky Way, which is not true in a lot of the US. Um, and then there's a bunch of scientists that are involved with a whole bunch of different things, from galaxies and clusters of galaxies to individual solar system objects and comets and asteroids and meteorites and so on. Um, yeah.
So in your work, what does your sort of day-to-day focus sort of look like, and then are there particular areas of research that you're pursuing as well?
Yeah, I'm mostly interested in the icy objects in the outer solar system, and that's partly opportunistic because they're farther away and they're harder to study, so there's more that could be done. Um, I'm interested in the materials that they're made of because at low temperatures the materials can have interesting properties like that two liquid thing that I showed. Um, uh, and well, you know how metal alloys are. You can mix two metals together, and if you get the proportions right and you get the temperature history right, you can really change the mechanical properties of it dramatically. Um, and of course, that's been economically important to study that. But the materials in the outer solar system, nitrogen, methane, carbon monoxide, water, carbon dioxide, and so on. They do similar things with similar complexity, but it's just not particularly economic to study them. You're not going to make a breakthrough uh, patent and become a millionaire from that, but they're quite fascinating, and the techniques that have been developed for material science purposes can be applied to them. And so, I go down the street to the university and talk to their material science people and get all kinds of ideas for how I could learn more about, you know, what kind of geology can these materials do for me.
Oh, fascinating. Yeah, it's interesting. I mean, right. I mean, how can you potentially experiment in a maybe even a laboratory setting to see, what shape do some of these things take in other environments? That's fascinating. Well, maybe hey, just a couple more questions here. We have another question from Bill who's curious. Does Mars have a similar layering as we have on Earth, where temperature down goes down to the tropopause, then up as you go up, or does temperature vary more continuously? What about other planets? Is that layering we have on Earth unique? I think you mentioned a little bit about some of the differences earlier on some of the maybe outer bodies there, where temperature, I mean, even in our atmosphere, different layers, temperature may either rise with elevation or cool with elevation, depending on
Yeah,
layer.
yeah, that's a really good question, and there's been a lot of work on that. I had a nice plot that I didn't put in one of my slides, and I'm going to just bring it over here. So these are the temperature profiles on 4 planets. Um, and so you can see the Earth in the troposphere, it's cooling as you go up. And that's true pretty much everywhere. But then you get these other effects. And in general, when you see these oscillations in the temperature profile, that tells you where energy is being deposited or being removed. Um, so there's a source of cooling or there's a source of heating. Um, and we do have Mars on there. And I guess the dashed line is for dust storms and the solid line is for normal conditions. And it does look like it's bending over up here, but it looks like they also cut it off before they get up into the thermosphere. Um, so I guess I don't have a great answer for you, but yeah, all of them have these kind of characteristic profiles, and often they have interesting shapes that tell you something about what's going on.
Oh, fascinating. Yeah, and you can see just in there the comparison Titan and Earth and some of the similarities, but unique differences as well.
Right. The other thing is take a look at that altitude. So Titan's atmosphere is just really, really thick,
Yeah,
whereas Earth's, so maybe by the time you're up at 100 kilometers, you might as well be in space. Uh, it's quite thin,
yeah.
whereas on Titan, you have to go up quite a bit higher.
Oh my
And
goodness, more than 10
so that's
times. Yeah.
partly because uh, well, mostly it's because the gravity is smaller, so it's just not being as compacted together.
Interesting. All right, well, maybe just one more question here, because I'd love to leave people on a note of where to learn more, and certainly what to look out for. I mean, I'm sure you are following all sorts of active research within astronomy, within space exploration, all that. I mean, above and beyond the work that certainly you're focused on, are there any upcoming missions that you're aware of, certain projects that you think, at least for our public and this audience, that we should really be keeping our eyes out for right now?
Yeah, yeah, I would say so. I mean, Venus is an interesting object because in many ways it's a lesson to us of what can go wrong on a terrestrial planet if you put too much CO2 in the atmosphere. I mean, we're not close to doing that yet, although we're certainly headed in that direction. Um, but a bunch of spacecraft are on their way or are soon going to be on their way to Venus. And it doesn't take super long to get there because it's close. Um, and not just the Americans, there's a European spacecraft, there's a Japanese one. So we're going to learn a lot about Venus in the next decades or so. And I think that's going to be interesting because you know, I, I couldn't point to any condensables that are on the surface, but there probably are things that are condensable on the surface, and that will be important. Um, there's some hints in some of the radar of Venus of something that's radar reflective being up on the peaks of the mountains. And it's almost certainly something that's condensing out of the atmosphere, but only at the cooler temperatures at the tops of the mountains. So I would love to learn more about that. Um, but NASA's got a very interesting program of exploration for the outer solar system. There's a spacecraft due to be launched to Europa in a month or so.
Yeah.
Um, and the Dragonfly spacecraft that I mentioned in another decade. Um, yeah, lots
Yeah,
of small
no,
body spacecraft also. Yeah,
yeah.
lots of stuff coming up.
Oh my goodness. Yeah, I know. Well, that's why I had to ask because I was curious what is specifically on your radar because there's a lot, including specifically, yeah, I think the Europa Clipper you're mentioning that'll be I think just in a few weeks here if all things time out.
Right.
Um, well, fascinating. Well, Will, I really appreciate you sharing your knowledge tonight, giving your time to our audience to share a little bit about your knowledge, what you study, what's going on at Lowell Observatory as well. Um, really appreciative of that. Appreciative of all of you in the audience for joining tonight. If you enjoyed tonight's free program, we strongly encourage you to make a donation over at mountwashington.org to keep these free and open to all. You can find the donate button that's right in the upper right-hand corner of our homepage there. If you have thoughts about tonight's program or suggestions for future programs, this was a great suggested program that came from you all. Please make sure to take the time to fill out the Google Form survey that'll show up in the Zoom window as you exit, and also in a follow-up email tomorrow for those of you who joined through Zoom. And then don't forget to join us for next month's Science in the Mountains program. That's on Tuesday, October 29th. And by popular request, because of what you've been asking for in the surveys, Mount Washington Observatory's weather observer and education specialist Alex Branton and her crew are going to give you a behind-the-scenes look at what a so-called day in the life, what a typical day might look like for a weather observer on Mount Washington. So make sure to come to that program with lots of questions. It should be a great one as well. So don't forget to register for that program or watch any of the other ones you may have missed over at mountwashington.org. And have a great night, Will. Thank you again so much. I really appreciate it. It was nice getting to connect, and hope we will talk again soon.
My pleasure. Bye
Yeah,
bye.
have a good night. Take care, everyone.